Thank you very much for coming. I'm sorry for all the rushing around. They were actually debugging things in the other room to do with the AV. Those of you who were in the SysMin mini-conf yesterday will have heard that Thomas unfortunately had his flight scheduled 24 hours later, and so he only arrived for the very, very end of the mini-conf and couldn't give his presentation. But we wanted to give him a little opportunity to give his presentation now. So without any further delay, Thomas talking about his large data storage projects.
Okay, thank you. It's possible to complete it even with a smaller audience here, but I think if you are here at lunchtime, then you are probably interested in the subject. So what I'm talking about, as always, I start with a small agenda. Well, this presentation was for 20 minutes. Now we have more time, and we have more time for discussions. Well, okay, it depends, but I will stay in time, at least for this presentation. And later we will go to discussion mode, like in the Birds of Feather session. Well, motivation, here's already the short main motivation is data growth, more than 20% per year. And I will explain what it means for our sharding architecture. We have one for decades. And later in the discussion, we can come to the topic why we have this architecture. But for this sysadmin talk, which is about hard facts, I don't talk about architecture now, but later the discussion could be about it. Okay, these are the main data where I'm working. It's web hosting, and shared web hosting means that many customers are on one physical box, or in one container we have 10,000 of customers, 10,000 of home directories. And in total, we have around 9 million of home directories. The domains are somewhat smaller, only 5 or 6 million or something, because many of them are probably not in use, free gifts. If you have a domain at 1&1, then you get a free web page, but some people don't use it. But nevertheless, some customers are very heavy. The biggest customers have 2 terabytes per customer, the biggest ones. And of course, you have millions of very small customers. So the range between the smallest home directory and the biggest one is several orders of magnitude. And as you can see here, billions of inodes. It's a challenge for backup during 24 hours. We have special kernel patches there because the normal denotify, inotify won't work because it doesn't record the old path for rename operation. So I have some special things there running. And the 4.5 petabytes is the net data. If you type df, I have the next slide in more detail. That's allocated space, and at logical volume level, we have a little bit more. It's about 8 petabytes, and all of this times 2 for geo-redundancy in total. And in 4 data centers, some in US, some in Europe. Okay, and the main point here is the growth rate and what to do here with this growth rate. So this is real data as measured. Hopefully it's good enough to see on, can you recognize it from the backbenches? Okay. So the unit is 10 power 12 kilobytes, so this is petabytes, okay? And this means the x-axis is days in the past. 0 was the 1st of January this year. And well, the statistics not going farther at the moment, but you can see what it means. Interesting is these lines here. The upper lines, the one is DF, and the other one is disk usage, summed up for customers. And there's a small difference for root space and configuration and similar things, of course. Yes, it's clear. And these ones are customers to a certain size. So these are the space growing the highest growth is customers which have more than 250 gigabytes per customer. And that is interesting. One of the many reasons is that some customers are using it as a backup space for doing the root server backups there. But if they have a root server contract, you won't kill those accounts, because you are earning money with it. So provided it's a very fast and easy backup for them, and it's okay. In the meantime, they have the technical means to deal with that. Okay, now the so-called efficiency project. I'm talking about hardware, very old one, which is up to 10 years old. And the old design from 10 years ago was having so-called iStore head, which is an HP box, and external RAID enclosures. And at this time, it was about 20 terabytes. The very first were even 10 terabytes with 300 gig disks and so on, 48 spindles, several spindles per RAID enclosure, and IBM blades, 7 per cluster, and connected via iSCSI to this RAID box. So you have 7 LVM logical volumes there in ordinary case. And the efficiency project means replace it by a very new hypervisor in one H unit. So you have a RAID with only 10 or 12 spindles, but about the same size. And migrating means how to migrate the data there with minimizing customer downtimes. This is what my talk is about, minimizing customer downtime for this case. And the business case is very clear. Alone the power consumption pays it all, pays the hardware replacement. You can imagine, if you have this high number of power cords and power plugs there, and power consumption is, I think, 1.6 kilowatts per old cluster, the new one is far better, it's clear. For sysadmins, it's very clear. So the business case, it's even better performance in total. So there's no single dimension which has gone worse. All dimensions are better than before. Okay. Now, first of all, the football migration project has several operations. Most important is the migrate, which uses MARS for data migration during operations. So the data is being ordered at the old system. iSCSI is working, data is being updated, and while this is all working, you are creating further replicas. It could also be done with DRB version 9, theoretically, but I have not checked. Migration during operations is something which I know is only, there's only 2 open source implementation I know of, it's DRBD and MARS. Okay. The shrink operation is necessary for those boxes because the very big customers, which are up to 2 terabytes, have been moved via rsync in a different project. And so we have a lot of logical volumes which are filled only by 20 or 30% anymore. And of course, you want to shrink them. And with XFS, it's a problem. You need a local rsync for that. While online resizing, increasing the size is no problem with XFS GrowFS. This is also automated in this toolset. And there are several combined operations like migrate plus shrink, and it means to save some network traffic. Because some people were fearing that the network would be the bottleneck, but it's not true. We reached up to 550 migrations per week. I will show you in the last slide. And the whole project is almost completed at the moment for 66 or 70% at the moment. So in half a year, we migrated several thousands of containers here. And the bottleneck is not the tool set here, but hardware deployment and decommissioning. You can imagine what it means to replace this number of in a specialized project. Okay, here's an overview about the process, how it works. So step-by-step instructions for sysadmins. It's very easy. In the original place, you have 1 or 2 replicas, and you are just creating. Here is the old side. No, we have no mouse pointer here. At the old side, you have 1 or 2 replicas. At the new side, you will have also 1 or 2 additional replicas. You are creating additional space at the LVM layer. Then you say MARS RDM join resource, and you create another replica. Do this 2 times on the 2 new sides, and you have 4 replicas in total. Primary remains the same, and they are waiting until the full sync, the MARS fast full sync has finished. And updates during this is no problem because MARS does it for you. Okay, and then a difference to normal handover between data center A and B. You are just switching the primary to the new one. Of those 4 resources, you can switch any one to primary. The other ones are automatically going to secondary mode. You just do it between clusters instead of inside of one cluster. That's the only difference to the normal operations, normal geo-redundancy operations. And then afterwards, you decommission the old side, and if it's emptied, you can, of course, decommission the hardware also for hardware lifecycle. Okay, any questions for that? Clear? Very simple concept, but the tooling, of course, is complicated in practice by many homegrown and very interesting problems there. If you have a system which is running already for several decades. 1.5 decades here. Okay. Well, next slide. Why doesn't it work? Okay, now. Well, here's one overview slide about the architecture of the football project. It's under GPL and on GitHub. And the gray parts have not yet been implemented. So these are my, including my plans, what I wanted to do. If I wanted not only to support XFS as we use at 1.1 at the moment, but also many other things, ButterFS, ZFS, whatever, and KVM, and even a DRBD here in addition to Mars. I think there are some guys around the world which could be interested in operating both, even alternatively or under the same tool set. I'm not sure. Is there any interest here in this room for such a thing? Okay. Well, what's already working is systemd as a cluster manager, but only in the lab. We have our homegrown cluster manager CM3, which means cluster manager version 3. This is for, well, it's not open source, so it doesn't help anyone, and therefore I have lots of plugins. And the plugin infrastructure is already prepared for extending for whatever in the world. So the project tries to be open, but it depends on you, the potential users, what will be done next here. Because at 1.1, of course, I have not the big motivation for doing this all of this. Okay, just a short notice about the strategy layer. The planned one is having a similar functionality like Kubernetes. That means an automatic migration plan. But at the moment, we are doing it manually with a manual planner because there are lots of hardware problems, hardware side effects, corner cases, where you want this particular box being migrated to a particular location and so on. And at the moment, it's done via tickets, very classical sysadmin way. Do you want to attend? No. Okay, here's the last slide here in this presentation, or the second last one. Current status, about 2/3 of the code is generic, and only 1/3 is 1.1 specific. So it should be adaptable to any other system in the world with relatively low effort. So I've tried to be as generic as possible there in order to be adaptable to whoever wants to use it. Well, the operations once again migrate and shrink and expand the 3 main operations and several combinations of it. Efficiency project uses it only for hardware lifecycle. What I should also note here is it need not be a one-to-one correspondence from one old cluster to one new one. You can migrate each resource independently from each other one. So of course the source can be split to whatever destination machines, and of course on destinations machine you can concentrate more than 7 resources. Interestingly, some guys are concentrating as much as possible. This means that the new average is around 9 or 10 resources now at the moment. So, well, the smallest containers are 300 gig, while the biggest ones are 30 terabytes. So it's 2 orders of magnitude between the smallest and the biggest one, and it's, of course, no single mapping is possible there for the very big machines. Our biggest machines have 300 terabyte in total on 38 spindles, so-called big food machines. So just as a side note, we have, at the moment, you have 2 different hardware classes for the new one, and we are planning having a mid-class in between. So 3 different hardware classes, different sizings, because most of the data is restricted by size and not by CPU consumption or by memory consumption. In general, you would have at least 3 dimensions. It's disk space, potentially also IOPS, it's a 4th one. Then, of course, memory and CPU consumption. But CPU consumption, most of it is static web pages, and PHP is almost the same. So the data space, the space occupation is growing much steeper than any other one of the other dimensions. So if you need to decrease the density somewhere, it's probably due to space consumption and not due to CPU overload or something. CPU is only loaded for about 50% in average at the moment on the new machines, having 7 to 10 containers. So this is not the real problem. If you have enough CPU threads, one new box has 15 times the performance of an old one. Newest generation from Intel at the moment, and we are planning to use AMD also. And this means, okay, it's no problem for having multiple containers. You just have to get your software ready for this. So that's the status. Then if somebody's interested, the short story, if somebody's interested, I think such a project makes sense if you have more than 1 petabyte of data. And if it's enterprise critical data. So if our use case, if my kernels would have a problem with consistency, probably the company stock exchange value would have a problem. It's clear because it's our main product which has most of the revenues coming from this. And this means you have to be very, very operationally careful in creating kernels and patches and so on and doing and so on. So I have less than 20 minutes, hopefully, or not. We have started later. So I'm in time with this. Now, you, Simon, is it okay to start a discussion, but you will be the leader.
Thank you, Thomas. My thought is, because it's a more general BOF, if anyone had questions for Thomas about his presentation, maybe we do those first, and then anything else that anyone else wants to talk about. So does anyone have questions about Thomas's presentation or Mars or football?
I was wondering where you keep the state for your volumes and how you know it's the latest one. Okay. Where is that being kept in your
the deployment? State of the volumes. The basic principle is to have the state locally. No central instance, because sharding means the sharding architecture is from databases originally. And if applied to storages, it means that you have no single point of contention. So if one of your shards is dying, even crashing, have a fatal crash, the other ones must not be involved at all. And this means the state is local LVM, stored locally. But of course, we have one central database where the state is also recorded, but it's not the actual state. It's like a configuration database. And this one is has low demands for access. And of course, in case of emergency, you could even reconstruct it from the physical state. So it's not the true state. The football project tries always not to work with some supposed state somewhere in some database, but always use the real state from the machine. So it goes to the machines via SSH and checks for whatever happens there or is exactly there. And if you have manual interventions from sysadmins, it adapts to the manual interventions. That's the key point here. Okay, it's not only about LVM state, it's about any other state. State information should not be in this football automation, so it's by concept, it's stateless. The state is in the machines, okay? But of course, for some states like, where should I migrate to? Of course, I need some state. But this state is kept to the minimum. That's the basic idea. Because keeping too much state in databases, which may differ from the actual state, is a major problem in operations of several thousands of machines.
So does that just mean the last written amount, so to speak? Yeah, well, if you're running your container, and that was the last live one, that was
container means stateful containers, not like Docker containers. This is a difference in concept, because the state is in the file system. So the machines, even the local configuration, so you can start independently from any database. So if you just migrate the data via Mars to another machine, the system image is updated via rsync, via so-called sync is indirectly from a golden image. And this means you are autonomous. All of your cluster nodes are autonomously handled by the sysadmin. So if something crashes at the network, whatever, in your central infrastructure, you are autonomous here. And this means for the football automation, don't use any central point of whatever. Or rely on it. You can use it, but don't rely on it. It's a difference. Okay? So the concept is really also applied to sharding, because if this, well, you have one central machine where the football is running at the moment, but I've developed it on my workstation, and if it's one central machine where it's currently running is crashing, just run it on your workstation. But of course, and it even uses locking, so there's no contention. It has local locks on each machine. It says so something is running, and it's constructed for contention. If several, yes. Let's go back to the architectural slide if you want to have some details. And the other screen now. Slideshow start from the architecture. This one. Okay, here I have, it's by concept, it's almost stateless, almost. In practice, well, there are some exceptions, but keep them as small as possible. That's the basic idea behind it, yes? Yes, it's very similar to the RBD. The Mars ADM commands are even very similar. So primary switch over is, you say Mars ADM primary resource name. And it automatically does the handover even for you. Very similar to the RBD. If you know the RBD, then you will have no major, but it's working asynchronously over long distances, and some commands may take longer because of this. Because propagation of state, of metadata state in Mars is solved very differently from the RBD. It uses a so-called Lamport clock, but this is my old presentations, some of them LCA. So if you look into my old path,
on the Sysadmin Miniconf site, if you look on the left-hand side bar, there's links to all the previous Miniconfs,
yes.
And there's like 2 or 3 talks by Thomas from the old presentations, which will have the slides there and should have the video as well. So
you will, these questions will be answered there. For this Birds of Feather sessions, I wanted to talk about architecture and big clusters like Ceph and Co. Versus sharding. And I have prepared another presentation, which is from FirstCon last summer.
Maybe before we do that, we see if anyone else has questions either about this topic or anything else that they want to talk about, so we can have a bit more of a general discussion.
Okay. But it could happen that you learned something you didn't know before.
Okay.
Yeah.
Hey, Thomas. Just wondering how this would kind of work with less than petabyte level data. Do you recommend it, or is it something that's just for larger data sets, like greater than 1 petabyte, or does it work well with, say, 500 or less than like 250 terabytes?
So your question is about the size of what exactly? Of the data or of the number of instances?
Smaller
yes, of course it works in smaller. It works in workstations. I know some sysadmins are using it over Fritzbox about DSL lines, just for backing up their logical volumes, because you have strict consistency in one of the volumes. And you have even strict consistency in your replicas, inside of one of your replicas, but you have eventually consistent between your replicas, your logical volumes, okay? But only in case of failure. If you have to do a failover, then you are eventually consistent. If you have a handover, then Mars waits for you until all the data is transferred, which is in the transaction log file. So it's, Mars is working very similar to MySQL, transaction logging replication. So it writes all the data to a transaction log file in the /mars directory, and then this is transferred over the network asynchronously. And it has no assumptions about the time. So it can take hours or seconds, whatever. Interesting is the downtime, by typically a few seconds, but for larger devices, because U-mount may flush out a lot of quota information, and it may take longer. And the downtime is much faster than if you have a local shrink operation with local rsync, and rsync is much slower because the last incremental rsync needs to be offline. Yeah. While the customers are not writing data anymore, and this one can take up to 20 minutes. If you have several millions of inodes in one file system, so there are some which has 20 millions of inodes in one instance, or even more. And then it takes a lot of time because it has to hunt, like find through all of these inodes recursively, and then means, okay, it takes some time. But we do it in order for long-term improvement of the whole pool. And of course, the Mars downtime is a matter of seconds. Most of the time is spent with BGP reconfiguration and similar things. Because if you switch to another data center or to another segment in the data center, you have to re-announce the IPs and so on, and this takes a small time, of course. So you cannot have zero downtime at the moment. And some guys at the FirstCon have asked, could I do live migrations? Yes, potentially I could, but from old hardware to new one, is it a good idea? Probably not. Okay.
I have another question, but I'll wait for if someone has another one.
If you have multiple devices with Mars, does it guarantee the order when it's doing replication? Because I think that's one of the things about DRDB, is it at least makes sure your disks are consistent in your sort of mirror site?
By multiple devices, you mean multiple RAID sets, or you have LVM? Well, in the next slide set, I have a picture for this, for your question. So get out of here, get into the other one. Oh, sorry, I don't have. In this presentation, I have it in the Mars manual.
Yeah, all I'm thinking is you've got, say you got 10 disks,
yeah.
You're using Mars to replicate those 10 disks to another site.
Lowest level is disks, then you have typically a hardware RAID controller. Of course, you can also use software RAID, but hardware is better because you have a BBU, and it's a very fast RAM cache there, which is very fast. Mm-hmm. Then you can have multiple. One of our machines has 3 RAID controllers, hardware RAID controllers for performance reasons, and also then you have LVM. You can have several physical volumes glued together to one logical volume group. So you have one volume group for user data.
Yeah, so you got multiple volume groups.
No, typically you will have 2 volume groups, one for system data and one for user data. Typically, it's better to have because the functioning of LVM is switching together multiple physical volumes to one group. This is the basic operation of LVM. And then out of this group, you can have as multiple logical volumes as you want. For example, we are typically using 10, but I think the maximum at the moment is 24 we are actually using. Mars is not yet scaling very well in this respect. I have to improve it, I know. It's on my roadmap to have at least 100 logical volumes because it's not scaling very well at the moment in this respect. But it will be improved during the next months or years.
Yeah, and I was thinking more, if you had multiple volume groups, multiple data disks, and you're writing to those data disks from your application, and that's been replicated to another site, okay. The write's going to happen in the same order on the other site. So if you lose it halfway through,
okay.
You've got consistency.
I understand what you mean. Okay, there's a similar demand from a few of our sysadmins which think that ZFS with multiple physical, from ZFS view, multiple physical, like using ZFS as a RAID substitute is a good idea. I don't think so, because, well, it's a potential new feature I could do, because I could do it. But it would mean either you have one central log file for all of this. At the moment, each resource has its own log file. It's completely independent from other resources, similar to DRBD. And I think this having...
DRBD supports the idea of consistent writing to different disks.
Yes. You have strict consistency in your local volume. And also you have fully strict consistency in your replica. So the order in the replica of applying the data is exactly the same as on the primary side. This is guaranteed.
Yeah.
So the only thing which can happen, you can have a delay over long distances. So if you have a power outage, you may lose something. Like as if the power outage were a few seconds or minutes or whatever before. It depends on the backlog. Okay? But you always have a consistent state, like a power outage at the wrong moment. And of course, if you have XFS or whatever, you have the transaction replay of XFS to repair whatever is wrong at the file system layer. Okay, so it's a generic thing on the block device level, but you can, of course, choose repair methods from the higher layers like file systems and so on. But at the moment, I have no tying of resources together to one logical unit. But this is a future feature I am already in my mind for several years, but not yet implemented. So if you want it, talk with me. Okay? It's not impossible. I know how to do it. It's one of the features we could talk about.
So it's almost quarter past.
Because there are some use cases like databases where you have the transaction. Yeah, this is a valid use case, very clear for me. If you have this use case, then talk with me.
It's almost quarter past, and I think people will start coming in for the next talk in a few minutes. Do we have any more questions or comments or anything that people want to talk about in the last 5 minutes or so?